Hello, in this video we are going to be running regressions using the dataset college distance from the Stock-Watson Introduction to Econometrics 3rd edition. So I'm going to read the data in first and just explain the variables very quickly. So we have a black dummy variable, so that's based on race. If I bring it over here, we can see it a little bit better. By-test is a standardized test score in high school. This is the county level unemployment rate that the student was in 1980. Did the student's father graduate college? This is the physical distance by 10 miles from a four-year university. The number of years of education the student obtained, whether the student was a male or a female. Hispanic dummy variable, is it a high income level? So I think this is from 1982 or 1983, so is it above $25,000 a year or more for the household? Did the mother graduate college? Did the student come from a family where they owned a home or were they renting? One if they owned. And then what is a manufacturing wage rate in 1980? The average tuition cost by state for public university, and then an urban dummy variable in there. So we want to just play around running regressions. So I'll close this, and to run a regression in Stata, you just use the regress command. So you can type in regress, or you can abbreviate it just by typing in reg. So you can just type reg, and then you always type reg, your y variable, and then your x variables, and then any options after a comma. So for a basic regression, we can just do how is education affected by, let's see, whether father graduated from college, mother graduated from college, and let's say the standardized test score for some sort of underlying latent smartness variable. So we're going to see how education is affected by these three variables, and we hit enter, and this is what pops up. So we have three general regions. The first one is telling us our sum of squares. So the total sum of squares is this. The residual sum of squares are the sum of squared errors, and then the model sum of squares, or the explained sum of squares, is right here. In this region, this tells us the number of observations, whether the model overall is significantly predicting education better than a mean. We have the r-squared, adjusted r-squared, and root mean squared error of the regression. And then this bottom portion is telling us our coefficient estimates, the standard errors, the t-test, the p-values, and the confidence intervals for each explanatory. So here we can see that education in this basic regression is positively and significantly, based on the high t-stat, affected by whether or not the father graduated from college. It appears that if their dad graduated from college, holding all else constant, they're likely to gain about 0.72 more years of education. For their mother, it's significant as well, based on the high t-stat and the low p-value. So if the mother graduated from college, the student is they're likely to receive about 0.41 more years of education. And then finally, the by-test, so the standardized test from high school, is positive and very significant. And so for every increase in the standardized test score by 1, the student was likely to obtain about 0.09 or 0.1 more years of education. So for a 10-point increase, that would be about 0.93, or about 1 more year of education for every 10 points higher in the standardized test. And then we have our constant as well. So that's a basic regression. If we want to go through, and we might want to, we could regress other things if we wanted as well. So we could just add in all the regressors. In this video, we're just going to be learning about some of the different commands though. So One thing is that these standard errors are homoscedastic. They're assuming homoscedasticity in the data. That may or may not be the case. So we could use heteroscedastic robust standard errors as well. So just go up here and we'll just rerun this regression, but instead of running it like this, we're going to use an option called VCE. So for variance covariance matrix, and we're going to go VCE and we type in robust. So this is for robust standard errors in there. So we hit enter. And now we can see, because of this, it's harder to figure out what our sum of squared is, so that it's dropped. But we have our heteroscedastic robust standard errors. And again, if we compare to what we found, the point estimates do not change by adding robust standard errors, but the standard errors themselves do change. So in this case, dad college and mother college become slightly less significant, or a slight decrease in the t-stats. By test becomes even more significant in this case. So these are going to be more generalizable if we do have heteroscedasticity. Finally, we may want to run something, and let's say that we don't want a constant. So here we're allowing the constant to float, or it's going to estimate a constant. Suppose that we think that the constant should be 0. We can force the constant to be 0 by putting in the no cons command. So it's going to say do not regress with a constant. So in this case, we're forcing the constant to be 0. So if all other x's are 0, y is expected to be 0 as well. In this case, it doesn't really make much sense, but we can still run it. And so again, we run this, and we still have all the variables here. But if we look, we don't have a constant because it's 0, or assumed to be 0, and we're regressing the slope terms without that constant now. And so we get a lot different results than we did before.